Hello? Hi, I'm Gary McTaggart from Valve. I'm going to talk to you today a little bit about our HDR implementation and give you an intro of why we implemented it, what it means to the players, talk about some of the features, reflection, refraction, tone mapping, and go through all the different steps we went through to get it to a shippable state. Okay. So first thing, why did we bother with HDR? First of all, we had all these great images that were generated by the guys that presented previously in offline rendering. They look really good. We wanted to get some of that into our games. Also, anytime we're thinking about a feature for our games, we're always thinking of what it means to the player and what gameplay implications it has. In the case of HDR, especially living in Seattle, you learn how important it is to go from a dark region to a bright region. And from playtesting, we've learned if you stick your players in dark regions for too long, they're not having fun anymore. So you have to occasionally throw them out into the light. And if it's a nice, bright, bloomy light that adapts over time, it's even better. There's some other things like if you're playing in a game and you're in the dark and you have your enemy out in the bright light and they can't see you but you can see them, that's really a cool thing. It's also a great mood enhancer for the game. So we implemented a demo, an HDR demo called Lost Coast that we shipped out in October of 2005. We had originally planned on implementing HDR and shipping it in Half-Life 2, but it turned out that it was just too much work. It took us a lot longer than we expected to get it working, so we ended up putting it off, and we decided that this Lost Coast demo that we gave out to all of our customers for free would be a great place to introduce it. So this is Jason Mitchell. He's also from Valve. He's going to give us a little demo of Lost Coast. Okay, we'll show a bit more of that in a little bit. Okay, this shot here shows a few interesting things. First of all, a lot of our lighting in the game comes from a few different light sources, like spotlights, point lights, and the infinite directional light of the sun. When we started working on using HDR in our games, it turned out that we actually could use less light sources with HDR than we did with LDR. In LDR, we ended up having to place all these little light sources everywhere to fill out the lighting. In HDR, especially in the combination with radiosity, this is lit with exactly one light source, and that's the sun. You get all the bounces on the sort of shadowed areas here just because we're using a radiosity algorithm. So we take these light sources and in our radiosity preprocessing tool, we compute what the HDR light maps are for the scene. This is a view here sort of to visualize the density of the light map texels in the world here. It's variable, and so each square here represents a single sample. So the primary HDR information that we have on our level, besides the light sources, the one texture that's actually hand painted that is HDR is the sky. We had originally started off by taking multiple exposure photographs like these here to do that, but it turned out that we got better results if we just painted them. We use a combination of HDR Shop and Photoshop to do that. HDR Shop, Sorry. HDR shop picks the exposure, and then you can paint in Photoshop. Unfortunately, the Photoshop products aren't quite there yet as far as painting HDR images. So this was also sort of our frame of reference for what we wanted our skies to look like. And this is the result in the game at 3 different exposures. And here you can see this is actually the authored skybox from this image. On the right is a fairly LDR-looking skybox that would look like something you would have seen in Half-Life 2 before we did any HDR work. So we took that and then we dropped it to a much lower exposure, and then we painted the sun in, so you can get the nice bright sun here even in the lowest exposures. So the next source of lighting in the engine are these cube maps. We use those for primarily for specular lighting. You can see here in our level editing tool, we've placed little samples on this pipe across this pipe segment here, so that we can get fairly accurate local lighting there. We end up using the engine to render the cube maps for us just by doing HDR rendering. And this is sort of a visualization. This is a visualization of just the specularity on these rocks here using these cube maps. Here's an example in Lost Coast that shows on the left there's the LDR version of the scene. That sandy, muddy, rocky surface there isn't particularly reflective. So in LDR, you don't really get any reflection there because the cube maps are only, they're low dynamic range. One of the interesting features, or one of our favorite things about HDR is on the right here, even though it's not a very reflective surface, the sun is really, really bright. So something really big times something really small can still be something really big, whereas we don't get that with our with an LDR solution. And we'll give you a demo of that now. So here we've sort of artificially forced the left to be closer to low dynamic range, although not completely there, in order to show what happens with the specular reflections, both on the water and also on the cube map surface there. You get much more pleasing results with the HDR reflections. Okay. Oops. Also, here's an example. I think I'm missing some slides. What happened here? Okay. Here's an example of another type of surface that we render. This is a water surface. We use 2 render targets to store the information for the reflection and the refraction separately. And then we combine those on the surface and do some perturbed sampling in order to do the water effect. One interesting thing to think about here with HDR is you have to also carry the HDR information all the way through that render target so that your final image can be HDR and reflect light in an HDR fashion. So like if you're underwater looking out, you really want to see the big sun blooming and refracting through the water surface. And here's a few different exposures of a water surface inside of Lost Coast. Another thing that we do is, in order to get a more general refraction effect that's not so special case like we do with the water, as we're rendering translucent objects from back to front, if it's marked as being refractive, we take a copy of the frame buffer to a texture, and then we render with that texture and perturb the samples so that we can actually refract what's behind that surface. And ideally, when you're rendering with HDR, you really want that data to be in high dynamic range so that if you have something like really dark stained glass with a really bright light behind it, you want to get a bright refraction through there. This is a scene from Half-Life 2 Episode 1, which we shipped a couple of months ago. You can imagine the player walking out of a dark scene out into this outdoor area here, and it's pretty overexposed looking, and their eyes adjust over time. This is 3 different exposures of that scene. Let me show you that a little bit in Lost Coast. Okay, another thing that we wanted to get in, I'll talk about the implementations in particular in a little bit here. We wanted to be able to put blooming in so that as they were talking about earlier with the bright side display, you want to get that blooming there to emulate what you see with your eyes. So here's a scene from Lost Coast without blooming. This is the blooming by itself, which is kind of this is generated by downsampling the frame buffer by 4, while at the same time multiplying the image by the luminance of the image, and then we do a 2-pass separable Gaussian filter. And this is the scene with the non-bloom plus the bloom, and this is the results that you get. So when we started doing our HDR implementation, we had a lot of criteria for evaluating the different methods. Some of these weren't immediately obvious, so this list kind of built up as we went. We started learning some of the trade-offs between the various methods. Whether or not the method would support multi-sample anti-aliasing was pretty huge. We try really hard not to ever step back in technology, and especially in visual quality. Since our LDR solution looks good with multi-sample anti-aliasing, and the customers see that as a huge benefit, we really didn't want to step backwards and not support. Okay, so we didn't want to step backwards on that. We also needed to support alpha blending. In a lot of cases, we tried approximations, but they just never seemed to work out. We have a lot of translucent geometry. We didn't really want to step back and stop using as much translucent geometry as we're used to using. HDR blooming is important, and that's in contrast with LDR blooming. You can still do an HDR method and still do LDR blooming. We'll talk about that a little later. Also, special effecty things like reflection and fraction have to work in HDR. Bilinear filtering has to work properly. One thing that we do regularly is we do a hardware survey to see what hardware our customers have, and we use that a lot anytime we're looking at any engineering task to decide what's the best approach and what hardware we have to support in order to get to a majority of our customers. Another thing that we had to look at are memory requirements, which are actually really closely related to the next item, which is performance. We found our games typically use a lot of memory, and video memory in particular, and we found that as we were developing Lost Coast, that at some point you hit the memory cliff and your perf goes to hell and there's not a whole lot you can do about it. So methods that use less memory are definitely desirable, at least in the case of games like ours that use a lot of memory. And then performance in general, like pixel shader length, how much CPU is used for doing the work, etc. So first I'll start off here with our ideal implementation. In this case, you have all of your HDR resources here. The green arrows are HDR data. The red is LDR 8-bit data, or at least post-tone mapping data in this case. One thing you'll want to pay attention to in this diagram is the order of the work. In this case, everything stays in HDR all the way down, past tone mapping, past blooming, all the way down to the point where you're actually converting to a gamma space, 8-bit gamma space for the frame buffer. I'll be changing this as we go along for the various methods that we look at. Okay, so the first method that we tried, which we demoed in fall of 2003 when we still thought we were going to be able to get this in for Half-Life 2. The idea with this one is that you have an RGB value that's 8-bit, and then you have an 8-bit alpha that gives you a scalar for the RGB value. The flow here is in general the same as the ideal implementation. Let me get to the pros and cons of this method. Since we're using an 8-bit frame buffer, the most important thing, or one of the most important things for us, is that MSAA works. That also means it works on all DirectX 9 hardware. Or that doesn't also mean, but it does work on all DirectX 9 hardware because it doesn't require a blendable floating point render target or anything like that. We didn't do our tone mapping and blooming until later into the process, so we still have HDR data there. Alpha blending is really difficult because the RGB times alpha times 16 isn't a linear interpolable value, so that really messes up bilinear filtering and alpha blending. You have to do a lot of really tricky code there to even try to get that right. Also, there's an extra conversion of the frame buffer at the end of the process. That can cost quite a bit. Another thing that's kind of tricky with alpha blending here is that if all your textures are typically RGB alpha and your alpha channel contains translucency value, then you're kind of screwed and you have to have another texture for that, and you have to do another pass in general for anything that's translucent. Here's a shot of an antlion guard. This is from that first demo that we did of this way back when. One thing that's important to note here is the guard's head here isn't particularly shiny, but since the sun is reflecting off of there, you do get a nice bright hot spot there. Okay, so the next implementation that we tried is a little different. In this situation, we're using a thing called MRT, which is multiple render targets. We rendered 2 8-bit per component render targets, and also all resources are stored in that format, so that you have the visible range, and then you have an overbright range stored in a separate texture. There's some reordering that's happened here. First thing to note is that the tone mapping happens really, really early in this case. One interesting thing about the way that we implemented Half-Life 2 is we had this constraint where we don't ever add lighting in the frame buffer. The primary reason for that is that we want to be gamma correct. Any adds that you do in gamma space are completely wrong and they don't look good. So we end up rendering almost everything in DX9 in a single pass. And we use the hardware feature sRGB read and sRGB write so that we can sample our textures in 8-bit gamma space, convert for free almost hardware to linear space, do the math, and then write it back to gamma space for free on a lot of hardware. Since we already had that limitation, that gave us the ability to do the tone mapping and the shader itself before we hit the frame buffer. Our tone mapping is just a simple, in this case, is just a simple linear scale in linear space. And you know that turns out to be a pretty good tone mapping method for us. We're not trying to get detail all over in the image. We're just trying to get some drama. When you see a nice bright image, you want to see it bloom, you want to see it wash out. So that works pretty well for us, and it's extremely cheap. Let's see. So in this case, the frame buffer itself has the LDR post-tone map LDR data in the low channel, and then the overbright in the higher channel. Yeah, we'll go on to the next one. So let's go to the advantages and disadvantages of this one. The main reason for wanting to do this one is that alpha blending works in this method. Bilinear interpolation works because we're just sampling textures as you normally would. It works on all DX9 hardware. MRT and MSAA don't play together very nicely, so that's definitely a big downside to this method. Another thing is the textures eat a lot of memory because you've actually doubled all of your lighting textures. You doubled the size of all of them. Okay, so at some point the 6800 GT came out, and it supports floating point alpha blending with FP16 format. So we decided to go try the most straightforward method that, as far as the diagram here goes, is really close to the ideal implementation. It was actually really easy to implement this method after doing all these really tricky methods. Good thing about this method, you get HDR blooming, you get HDR refraction, you can look at your whole final frame buffer in HDR space before tone mapping to do your tone mapping, and do some more elaborate stuff there. On the downside, a lot of hardware doesn't support floating point alpha blending, even if they do support floating point formats. Performance was really bad. The first gen of FP16 blending hardware isn't particularly fast. It eats a ton of memory, not only from the source textures, but also from the intermediate render targets are all twice as big as they used to be. So in a lot of cases, this would push us over our performance cliff, and we'd have to cut back on texture usage. Biggest thing is that MSAA doesn't work. If it weren't for the perf and the MSAA not working, we'd probably be using this method right now. Another sort of aside, one huge gotcha if you implement a method like this is that for some goofy reason, the hardware is implemented with to support floating point specials. What that means is you write your floating point values that are 16-bit and really easy to overflow. You write those into your frame buffer. You add some lights into your frame buffer. By the way, that's another good feature of this method. You can add in linear space lighting into the frame buffer. So anyways, you overflow your values. You go analyze the frame buffer. You do a pass over the frame buffer to see what the luminance is or to get a histogram. And then all of a sudden, your frame buffer has infinities in it. So the scene is infinitely bright. You do your tone mapping, and it's infinitely dark. And if you're doing that in sort of a loop as a feedback mechanism, then you're completely screwed. And there's not a whole lot you can do about it. So that's a big downside to this method. So the next method is what we ended up shipping with, and it's what we've shipped from Lost Coast on, and our future games are using this. It's kind of strange in that it's actually using an 8-bit frame buffer. That's mainly because we want to get anti-aliasing out of this, and we also want to get some performance. So here, like the two buffer method that we did way back, we're tone mapping in the pixel shader in all of the pixel shaders. Like at the end of the pixel shader is just a linear scale before you convert to gamma space before writing to the frame buffer. So you get to this LDR frame buffer post tone mapping. We do blooming off of the LDR, off of the already exposed frame buffer. And the other thing worth mentioning is that our refraction can't keep the HDR data because it's actually copying from a post-tone mapped LDR frame buffer. Okay, so the good thing about this, it works on all of the hardware, all the DX9 hardware, which when we shipped Lost Coast, that was about 60% of our customers. And for the first couple of months of players for Half-Life 2 Episode 1, that's about 83% of our customers that are able to play with HDR, so that's pretty cool. Doesn't take a whole lot of memory. All of our lighting textures are either integer 16 or FP16, depending on if the hardware does filtering or not. The render targets aren't any bigger than they were in the LDR solution. It's very, very fast. It's almost not measurably slower than our LDR solution that we shipped with Half-Life 2. As an interesting note, this laptop here is running a Mobility 9800 from a few years ago, and if we were using the FP16 solution, I wouldn't be able to run it on here, but it actually runs pretty well on here. Also, there's no specials to deal with. Now, the two big things that come up with this method is when you're doing blooming, you have to do it using the already tone mapped 8-bit gamma frame buffer. That seems like it would be a pretty huge problem, but refraction doesn't happen in it doesn't keep the HDR data through the refraction. They copy from the frame buffer. In the case of water, we dealt with that by by not only tone mapping on the way into the render target for the reflection and the refraction, but we also multiply by 1 over the specular factor, or the K reflection, for the material, so that we actually maintain the full range of HDR data that we need to get the sun reflecting in there. So that works out pretty well. In the case of the general refraction, blooming gets us part. We don't actually get true HDR refractions, but blooming gets us part of the way there. Like in this case here, this actually isn't an HDR refraction, but it still looks pretty good. Do you want to show that, Jason? So here you can see that it's actually refracting what's behind the glass here. If he shoots it out, then you can see the data that's behind there. Okay, so I'll get to this slide in a minute. We're going to show you a demo first of this before we get to that. Oh, you want to load the courtyard? Okay, we came up with a pretty neat way to do auto exposure. You can see this graph up here. We have it has buckets in it. The height represents the luminance. Actually, the height represents the number of pixels at a particular luminance range. You can see that the buckets are actually different size. That's because we wanted to get more information at the lower end of the buckets. The way that we get this information is to we end up having to get our information for doing auto exposure out of the already tone mapped image, because that's what's actually in the back buffer. So what we end up doing is at the end of the frame, we draw passes over the whole scene. We draw a single pass over the whole scene, which generates an alpha test value from the pixel shader. If it's within a given range, it's set to 1. If it's out of that range, it's set to 0. If the alpha test passed, then it increments the stencil value in the stencil buffer. We do another pass where we use the asynchronous occlusion query feature of the hardware to count up how many pixels were actually in that range. Every frame we update a single bucket in this histogram because we don't really need the data immediately. We just need sort of a general idea of what the histogram was in the last few frames. Plus there's a whole lot of smoothing on the data anyways, so having every bucket, every frame isn't exactly necessary. So without getting any stalls from reading that back frame buffer from the hardware or anything like that, we end up getting this histogram. So instead of just working off like a general luminance for the whole scene, which we started off with, we actually have a lot more data to work with here. Okay. So here's this is from the similar scene here. This is actually a visualization of the red are pixels that were in a particular luminance range that passed the test. You also notice the rectangle around the whole thing. We only do a square in the middle of the screen so that it exposes the same no matter what your aspect ratio is. Here's another range. It's just a calculation of another one of those buckets in the histogram. Okay. So as I mentioned earlier, our tone mapping is really simple. It's just a linear scale at the end of the shader. That seems to work pretty well. This is 3 different exposures of another scene. So from listening to one of from the tone mapping topic earlier, there's a whole lot more you could do with tone mapping than what we're doing. One thing that we've thought of recently that we'll probably put in is we do a color correction method that's similar to what Drew was talking about, where we have a 32 by 32 by 32 volume texture that we use to translate our final image into another color space. And So basically, that's a gamma space conversion. We use Anyways, we go from gamma to gamma on that one. We have enough samples there that it works out okay. We use this in our games. Anyway, what I was getting at is when you're doing tone mapping, when you're in a really dark room and you're really, really highly exposed, you really want you want to desaturate your image. And we could detect that situation even with our simple linear tone mapping and use color correction to do that work after the fact off of the 8-bit frame buffer. Here's an example. This is being used for a different reason. But this is our game Day of Defeat. It's a World War II shooter. And basically when you die, we use color correction to put you in a sort of an archival footage mode. We put some film grain on top of that as well to make it look like an old movie from World War II. So as far as our authoring goes for our HDR levels in games, we first off just tried to use auto exposure and the blooming and let it do its thing as you might expect. We ran into situations where things would look too overexposed, underexposed, or there were cases where just for drama we wanted to overexpose things. So we added a bunch of entities to the levels where you can actually set the range of exposures, and you can also tweak how much blooming you get, etc. We also do asymmetric auto exposure like the eye. So going forward, we've also been experimenting with using non-photorealistic rendering in Team Fortress 2, along with HDR, since we're using the same engine. So here you can see, these guys look fairly NPR'd, but we're still able to get some HDR goodness out of it. So in overview, we talked about HDR, why we did HDR, how we got started on it. We talked about reflection and refraction issues with water and general refraction. Talked about tone mapping and auto exposure in real time, and also how we got to a shippable implementation of HDR. One thing that I wanted to mention is we have a freely available SDK. So if anybody in the academic environment is interested in using that for their students or otherwise, you can download that for free as long as you have a copy of the game. You can use it to do pretty much whatever you want. We also have academic pricing for the game as well as licensing. If you want to do it on run a server, $10 a seat, it rolls over to other students when they're done using it, etc. We give you a lot of code for the shaders, the AI, pathfinding, animation system. We give you all of our art, or at least a lot of our art resources, models, and animation for the games as well. If you're interested in that, that's the email address there to send to, or you can just send to me. Any questions?